Alrighty, time to start chapter 26 of physics for Finlandia University. In this chapter, we'll be discussing geometric optics, or looking through a lens of some sort, or I guess reflecting off a mirror too. This picture is an example of, well, as I said, geometric optics. Why does the reflection off the lake look as good as it does? We'll discuss the math behind that. In this chapter, we'll be discussing these particular subsections: reflection of light, images in plane mirrors, spherical mirrors, ray tracing, refraction of light, ray tracing in lenses, the thin lens equation, and finally, rainbows. So, how does light work? Well, rays of light propagate out in a circular pattern similar to dropping a stone in a pond, i.e., they go in all directions, where the ray front is defined by these arrows here. As you move further away from the point source, the wave fronts become more and more flat. Essentially, as you watch the spherical wave fronts, the total curve of the wave becomes less and less as the wave itself gets taller and taller and taller. This allows us to use things such as the law of reflection. The law of reflection states that the angle of incidence is equal to the angle of reflection. We talked about this a bit in lab earlier. If you point a light source, such as a laser beam, at a mirror, it will bounce back the exact same angle that it hit. Incidence would be where it hits, the little I. Reflection would be the R, or the bounce off from it. Why mirrors work so well and other surfaces do not is a specular versus diffuse reflection conversation. With a mirror, a smooth surface, such as, again, a mirror, specular reflection occurs, wherein all the rays bounce back at the angle of incidence. B, showing a not smooth surface, something that doesn't reflect well, paint, wood, things of that nature, all the rays of light bounce off the surface, but they all bounce off at different angles, so you're not getting all that light in one location like you would with a mirror. So how do we form an image with a plane mirror? A and B show you examples of that. The light that struck the flower initially reflects off the flower towards the mirror, and that mirror then reflects all that information into your eye. So much so that all these angles down here in B, A, D naught, DI, phi, theta, stuff like that, these all work in conjunction to tell you, when you look in the mirror, how does that image that the mirror is producing reflect reality, right? If you look at the mirrors in your car, objects in the mirror are closer than they appear, right? Why are they closer than they appear? Well, that's to do with the way these mirrors work. It all follows Snell's law. The difference is depending on all these variables we're showing here. You do homework examples of this. Properties of mirror images produced by plane mirrors. First thing to notice is that a mirror image is upright, but appears reversed left to right. So if you move your hand to the left, it appears as though your mirror image is moving their hand to the right. But good for us, the mirror image is to upright. The mirror image appears to be the same distance behind the mirror that the object is in front of the mirror. And again, look at a mirror, step back, what happens? The image the mirror produces also steps back. And they're roughly the same size. Again, this depends on other various things, but when you look into a mirror, a flat plane mirror, you see something that is a very one-to-one. Oh, okay. Cool. So that's how plane mirrors work. How do corner mirrors work? Well, as shown here in this example, a corner reflector reflects light parallel to the incident way, no matter the angle. Because all of these three dimensions of mirror all follow Snell's law the same, giving you a total response to that mirror that is parallel. So when you look in a mirror, mirror looks back at you. We can also discuss spherical mirrors. A spherical mirror has the shape of a section of a sphere. You actually don't, like, bowling balls that are made of mirror aren't actually what we're talking about here. We're talking about complex and concave sections of mirrors. So we're not talking about the big bowling ball here. We're talking about the little insert. All these spherical mirrors, those little sections that we talked about, have a central axis that goes along with the radius of the sphere. They also have a center of curvature pointing towards the center of the sphere. This allows us to delineate concave and convex mirrors. Parallel rays in a spherical mirror come together at a focal point, or appear to have come together at focal points. The mirror is convex. Again, we can look at what's going on with this example here. We have the light rays on the left here flying in parallel, and they are reflecting radially out. What happens when they reflect radially out? The image itself follows those reflection lines coming to a focal point. So at this point, things reflect at the best way they can. Ahead of or behind the focal point, things will change depending on what type of mirror you have. So focal point is very important because that's the sweet spot for a spherical mirror. Again, we have a concave mirror doing something similar to it, right? Picture concave and convex mirrors. What do you usually use a concave or convex mirror for? That will tell you the point of the mirror, and it will give you a little bit of an example. If we were in class, I'd pull out a concave and a convex, and you could have fun with them. But honestly, in your house, you have examples of both. Try to find them, move them back and forth, see what happens to the image. It can be pretty interesting. Or if you can't find anything, find a YouTube video demonstrating this concept. The focal length of a convex mirror of a certain radius is given by this equation here. The focal length is -1/2 of that radius. A concave mirror, by contrary, is the positive half of that radius. Negative and positive here? Well, that's where is the image in relation to the mirror itself, right? This is because the focal length is negative as the rays do not go through the focal point. Opposite is true for concave. And if you go back to those images prior, you'll see you can connect this equation to that image. We have made this assumption here that the rays do not hit the mirror very far from the principal axis. If they do, the image is blurred. This is called spherical aberration. It can be remedied by using a parabolic mirror instead. So what this is describing here is the amount of bend you put on the mirror will help it balance to where it needs to be balanced. Makeup mirrors have a certain bend to them such that the usual place you would put the mirror focuses exactly where it should focus. If the makeup mirror was too little or too far bent, it would be much less usable because you wouldn't be able to hold it away from your face at a reasonable distance. When the Hubble Space Telescope was first launched, its optics, wow, that was a tough sentence, were marred by spherical aberration. This was fixed with a corrective lens. Satellites themselves have to undergo routine optics. They have to go to the optometrist to get corrective lenses put in place. All these rules still apply. And again, this would be a good example. Look at this image. Look how large the people are compared to how large they are in the image. And notice that you have these two people in the foreground. Do you even see them? No, because the four people in the mirrored image are all standing. Now we can get to ray tracing, something that I argue is kind of fun. You may disagree with me. Use three principal rays in finding the image produced by a concave mirror. The parallel ray, or P ray, reflects through the focal point. The focal ray, or F ray, reflects parallel to the axis, and the center of curvature ray, or the C ray, reflects back along its incoming path. The P, F, and C rays allow you to understand what a mirror is going to produce and how it's going to produce it. These rays, of course, are illustrated here, caring about the focal point and the, what's the C ray do again? Center of curvature. There we go, yeah. And the center of curvature ray. Images are formed using these three rays, and you use these three rays to form images of convex mirrors. The image is located where the projections of the three rays cross. The size of the image is also determined via this amount. So we have our object here on the left, tall red arrow, tall, thicker red arrow. And we notice the object on the right, the image shows up before the focal point and is shorter. And this is because if we follow all these rays off of where we're looking, essentially your eyeball is the top of that mirror, you make the P ray parallel to you, bouncing off, and that ray, that incident angle cuts back down to the center. You got the C ray, which points towards the center part, right? That goes straight through with this particular section. And then you have the F ray, the focal point, looking at the focal. The way that bounces, again, according to the angle of incidence, angle of reflection, these three rays come together at the head of this dashed arrow here, creating an image that you can calculate its height and its distance from the mirror. The process is similar for concave mirrors, although there are different results depending on where the object is placed. This is what I was talking about. It's good to find examples of concave and convex mirrors, look at them and move them back and forth and see what happens. Because as we notice here, depending on the location of the object, we can have a very differently sized image, all following the exact same rules, but the way the mirror bends and shapes things contorts the image differently for the same object. All this fun math can give us mirror equations. This may look super difficult, but in practice, mirror image equations are not very hard. So this might be a good thing to note in your textbook. So when you go over the homework and stuff like that, you can correlate the variables in the equation to the physical representation shown here. We can use those triangles and the equation F equals 1/2 R, where F is the focus point and R is the radius, to give us a mirror equation for distance. D naught is the distance you are standing from the mirror, and DI is the distance that the image is standing from the mirror. And F would be the focal length, again, given by that equation up top. Here's a nice little chart explaining what different mirrors do and how they change things, enlarging, reducing in size, inverting, upgrading in image, and then what type of image you're talking about, real image or a virtual image. Magnification follows the change in height or the change in distance. So if you want something to make the height very much different from what it actually is, use different magnifications. Here again, a nice little chart giving you focal length, magnification, image distance, and object distance in relation to the type of mirror and the type of image that you're talking about. This may be useful, this may not be useful. I find the equations to be straightforward enough that this cheat sheet stuff might not be useful, but it's your prerogative. It's in the book. It's on the slideshow here. So let's do an example from page 927. Santa Claus notices his image in a Christmas ornament. Shiny Christmas ornament, right? We all probably have a silver ornament on our tree at Christmas time. This ornament has a radius of 4.52 centimeters and is 0.866 meters away from Old St. Nick. When Kris Kringle looks at this ornament, where and how large is his image, given that he himself is 1.76 meters tall? So when he looks at the ornament, how big is he in the ornament, and where is he in the ornament in representation to the image. So where is a distance calculation given by the equation we just showed before, 1 over di equals 1 over f minus 1 over do. But in order to solve that, because we know do, we're trying to solve di, we need to know the focal length. Well, again, as stated previous, focal length is the negative half of the radius. So plug that math in, we get a focal length of negative 0.0226 meters. Once you know the focal length, plug it into the equation, solve for the inverse, we find that Kris Kringle's image is 0.022 meters inside of the ornament. He is 8.866 meters away, but the image is 2 centimeters inside of the ornament. And right, the ornament's not going to have that much of a difference. Well, sorry, the ornament's not going to have as much of a length necessarily. That makes sense. To figure out how tall he is, we use the height equation. We need to know magnification in order to use the height equation, so we can figure out magnification because magnification is given by either height or distance. Plug in our image and our original distances into the equation to get magnification of 0.0254. Notice here that the math for solving for magnification leaves magnification unitless. So plug a magnification into original height, 1.76 meters. We get out an image height of a little over 4 centimeters. That is how big and how far away St. Nick is within the Christmas ornament. I'm glad he knows that. Refraction. Talked a lot about reflection. We can talk refraction now. Since light moves at different speeds to different mediums, when it travels from one medium to another, the change in speed causes the ray to bend. It's going faster or slower. This change happens. This is, again, Snell's law. This is something we did in lab, and it's also something that you're very well aware of. This is why the straw looks in different places in the glass of water. The angle of refraction is related to the different speeds. So if you know the speed in light, the velocity of light in the particular object, and you know the angle it's entering, you know therefore the angle it's leaving. The definition of the index of refraction, n, is given by the velocity is equal to the speed of light in a vacuum over n. Here are some typical indices of refraction, or how much light is bent by what you're looking at. Diamonds have a very large index of refraction. This is part of why they shine so well. Crown glass, fused quartz, regular glass, ice, all these things have decreasing indexes of refraction. So much so that when we get down, we go through some liquids, benzene, ethyl, alcohol, water, and come down to gases. Gases have barely any index of refraction, so little, in fact, that it's not really worth discussing to the human eye conversation. Looking through carbon dioxide, looking through air, to your eyes, to your perception, are essentially the same thing. But very different from, say, water, or ice, or flint glass, so much so that those cause very large changes in the ray path. And again, shown here, given Snell's law, given the angle of incidence, which is derived from the speed of light in a vacuum, you can figure out where something is and where something's shown to supposed to be. We did this in lab with the laser pointers. This is something you are, as a regular human person, are familiar with already. There's the math behind it. Basic properties of refraction. When a ray of light enters a medium where its speed is decreased, it's bent towards the normal. And when a ray of light enters a medium where speed is increased, it's bent away from the normal. There's no change in direction of propagation if there's no change in incidence of refraction. The greater the change in incidence of refraction, the greater change in propagation direction. So if you if the medium changes water, you have a less change of direction than if the medium change is, say, diamond. And that was shown in the picture previous, showing this picture here, right? comes in at 60, exits at 40 for water, comes in at 60, exits at 20 for diamond. Diamond has a greater incidence of refraction, therefore diamond bends light more. And lastly, if a ray of light goes from one medium to another along the normal, it is undeflected regardless of the angle of incidence. So if you shine something along the surface, it's not going to bend. As I was saying before, refraction causes things to bend in water. That's the most common thing you've seen. I guess mirages work this way for anyone who has to deal with a mirage. If light enters a medium of lower index of refraction, it will always be bent away from the normal, as said before. If the angle of incidence is large enough, the angle of refraction is 90 degrees. At larger angles of incidence, light will be totally reflected, as shown here. Notice as we go from A down to D, eventually we achieve total reflection, where C, you have some refracted beam that is parallel to the interface of these two mediums. And this all ties into Snell's law, angle of refraction, things of that. It's just playing with the math. If you do get that total refraction, we call it, well, total internal refraction. And the incident angle at which angle of refraction is 90 is called the critical angle. The total internal reflection idea is used in things such as binoculars or fiber optics. They say optical fiber, but same difference. So what, for example, fiber optics are, is something that will pass light along its medium regardless of if there's bends or breaks in the light. If you have ever seen fiber optics in person, feel free to go to YouTube, look it up if you don't know what I'm talking about. It's a very cool thing to actually see for the first time, the fact that fiber optics bend light and send it essentially along a tube like water. It's pretty fun stuff. There's a special angle called Brewster's angle. This is when light is reflected that it becomes totally polarized. Reflected light is completely polarized when the reflected and refracted beams are at right angles to one another. The direction of polarization is parallel to the reflected surface. So this image over here shows we send in light at different angles. You notice the light here is in crosses, and then when it reflects off only polarized in one direction. Pretty cool stuff. You can find Brewster's angle by taking the tangent of the division of the indice angles of the materials you're talking about. I'm sure it's useful. I don't personally know what that is useful in the real world, but math is fun. So, lenses. Ray tracing for lenses. Lenses are used to focus light and form images. These are not mirrors because, well, you look through lenses, right? A variety of possible lenses. We will consider only symmetrical ones, the double concave and double convex. So here we can see converging lenses and diverging lenses, concave and convex lenses. We're only going to talk about the double of each. So essentially, we're not talking about the lenses that you put on your face. If we think of a convex lens as consisting of prisms, not a bad way to go about it, we can see how light going through it converges at a focal point, assuming, of course, the lens is properly shaped. Again, we can look at the prism, always bending light down, as shown here, and on the right, and the convex lens on the left follows the same principle, the same idea. We can also therefore model concave lenses on prisms in the way that they expand light out and where the focal point comes back to. The three principal rays for lenses are, unsurprisingly, similar to those for mirrors: the parallel ray, the P ray, the focal ray, or the F ray, and this time we have a midpoint ray rather than a center point ray. This goes through the middle of the lens and assumes the lens is thin enough that it will not be deflected. Examples, this should look eerily familiar, right? Showing what happens with these three lens types. Notice the focal point in the image location for the convex versus concave rays, and how there really isn't one to the right over there, right? Those three arrows are never going to meet. As with mirrors, you can use these rays to locate the image as shown previous. Cool stuff. There's lots of math involved. These things are kind of fun to draw, but they require a good use of the protractor and stuff like that. Create images, not create images, things I just said previously. More examples of that. Again, follow the lines, think about how the lines work and the way the lines work. And if you have any of these lenses at home to play with, please pull them out and play with them. You know, if you wear glasses, take your glasses off, put your glasses on, and you'll notice that focal, where things are most crystal clear, changes. The thin lens equation, again, lots of gross, nasty diagrams with lots of letters and variables on them that end up producing not very difficult equations. So this looks awfully similar to what we talked about with mirrors. That's kind of on point. That's there because of a good reason. Giving us very similar looking equations for focal length, distance, magnification, things of that nature. And another list of, again, very similar looking descriptions as to what happens. Focal length is positive for converging or convex lenses. It's negative for diverging or concave lenses. Magnification, object distance, things of that nature. Look at this if you want, but the equations always follow these rules anyways. Finally, we get to talk about rainbows. Yay. The index of refraction varies slightly with the frequency of light. In general, the higher frequency, the higher index of refraction. This means that refracted light spreads out because it exits the prism at different angles. This spreading out based on frequency causes rainbows. Water does this. As we all know, rainbows show up after a storm because of all the water floating in the atmosphere. It reflects out this way. And yeah, I've taken all the fun out of rainbows now. If you thought rainbows were still some magical, wonderful treat of nature, well, this is the final time they're not. They're water breaking up light. Sometimes you get two rainbows. Cool. That's a lot of water in the atmosphere. How exciting. So that was reflection, refraction of light in lenses and mirrors. Overall, a lot of gross looking diagrams to allow us to use lots of very simple equations. And we can just talk about the very basics of light. A wavefront is along a surface. A wavefront is a surface along which wave phase is constant. This is what we talked about before with the stones. Angle of incidence, angle of reflection. Knowing how those work with mirrors. How mirrors create images, how plane, convex, and concave mirrors create different images based on focal lengths and distances, following these equations shown here. Magnification images, talking about refraction, speed of light, index of refraction, things of that nature, Snell's law. Again, these equations aren't super difficult. We've left electricity, so we're kind of done with super ridiculous looking equations. But these are still very useful features, depending on what you want to reflect or refract. If you end up wanting to be an optometrist, you better be good at this stuff, right? Magnification, given refraction, rainbows are fun. And that's the end of chapter 26. So check your homework for, check online for your homework, get that stuff done. I'm planning on clumping 26 and 27 together in the homework to see how it goes. If that ends up sucky, you want to do individual going forward. We only got, I think, 4 or 5 chapters left, so we shouldn't have an issue with time. And, well, thanks for watching. I'll post this on YouTube and send you all that link as well. Take care.
Bye.